Okay, so the next little bit of 2.8, I think we're in 2.8, about this least squares regression line is how the least squares regression line is actually calculated. Obviously, we just put in our calculator and do lim regress, and same thing with other programs, but mathematically you could do this by hand. And the AP likes to have questions that show that you know how the actual hand calculations work. The nice thing is, if we go to our formula sheet, simple linear regression, we can actually see here they're giving us some information. Ooh, no, this is not what I wanted. Hold on a second. This is here in the inference part. We don't want to be there yet. It's got to be earlier. There it is. Sorry, it's in descriptive statistics. I was being slow. We have our y hat is equal to a plus bx. You'll note that they switch the order from what we get out of our calculator. The reasoning is for in a traditional linear regression setting, you might have multiple things that help you predict whatever your y is. So I'm trying to think of the last example we did, like the amount of iPhone sales. We could use the year. We could also use the price of the phone. We could, like, there's other things that we could use. And so, in statistics, we would then do that. We'll call this B1, and then we'd add in other variables. And so that's why in statistics, we swap the place of the intercept and the slope, is because we could have multiple predictors or multiple independent variables that we're using. So the other piece here, the other pieces that are our formulas, we've got the general equation for the line. We have that we can find the average y from the line. Basically, this gives us this information that the point x bar comma y bar, the average of the x's and the average of the y's, that is always going to be on our scatter plot. So if you looked at where the average for the y's and the average of the x's are, that's always going to be on your linear regression line. So that's what this is giving us. And then we can get the actual pieces to this linear regression line. And the most important formula here is that we can find the slope by simply multiplying our correlation by the standard deviation of our y's divided by the standard deviation of our x's. So that's that, right? If you have this and this together along with some summary stats, you can find A and B, right? This would be because if I have the SX, that's our standard deviation for our x's, and our x bar for our mean for our x's, and I have the same thing for my y's, you can see how if I have B and I have those means, I could go ahead and find my y-intercept. So these two formulas are used together in tandem a lot. The idea that we can find basically our whole linear regression as long as we have correlation and then the summary stats for our x's and our y's. So I have a question showing how this is used on our lecture notes. So we go here. This is a little bit different. That's why I wanted to show you guys that formula as it is on the AP, because on the AP, the formulas they gave you, y hat is equal to a plus bx, right? And so we didn't need a b1. This was just r of sy divided by sx. And then our y-intercept, they didn't set it up as easy to solve for our y-intercept. They gave us the regression line with x bar and y bar on it. And you can see that little note that lets us know this, but we don't need to know it because it's actually there on our formula sheet for us, that our regression line will always pass through the average of the x's and the average of the y's. So let's see how they test this. All right, this is a straight up question where, as I told you, you can see here we've been given the summary stats for our two variables and also our correlation coefficient. That means we can make the entire equation for the line. And in fact, that's exactly what we're looking for, the equation for the regression line. You'll notice that I'm pretty lazy, and most problems I go straight to the given information and straight to the last sentence before I get bogged down in the details up above. So right now, I don't even need to know what the heck this is about. And the fact that this is about a limnologist or whatever, which is a very strange word, and I could get bogged down trying to understand, I don't need it because I know I'm looking for the equation for the regression line. I'm going to write down those formulas from the formula sheet. We know y, our regression line is y hat is equal to a plus bx. I need to figure out my a and my b. And so the first one is that I'm going to find is my b. This is, according to my formula sheet, which I'll bring back, just r times sy divided by sx. So my r times sy divided by sx. And we have r, it's negative 0.98. We have sy, that's 30.8. And we have sx. This is a question from the AP, literally. And we just have to go ahead and say, let me get a calculator out. We've got negative 0.98 times 30.8 divided by 2.8. I guess I'll close my parentheses when I don't need it. So 10.78. So, all right, and then we need our A. This is where we're going to use that second formula. So looking at my formula sheet, we're going to use this one. Y hat is equal to A plus B times, or not Y hat, Y bar is equal to A plus, so Y hat is equal to A plus B times the X hat. I keep saying hat, bar, can't do it, Y bar. So Y bar, well, that was given, 37.6. Our A, we don't know, that's an equal sign. Our B, we just found, that's negative 10.78. And our X bar, well, that's 10.2. So if I want, I can go ahead and figure out what that is. 10.78 times 10.2. We've got 109.956, negative 109.956, or A. And then we do our bit of algebra here. We're going to add 109.956 to both sides. Woo! 109.956. So we end up with an A of, sorry, I'm trying to do this in my head, and that's a bad idea. There's a 5, 6 at the end. A 5, I'm going to add 1 to that, so I get a 7, add 1 to that. I think that's 147.556. I should absolutely not be doing this in my head, which means our final equation is y hat is equal to 147.556 minus 10.78 times x. So you could do plus and negative 10.78. But that should be our beautiful regression line for predicting the number of flatworms based on creek temperature. So we'd expect if the temperature was 0, there'd be 147.5 flatworms, and for every increase of 1 degree in our temperature, the number of flatworms will drop. So obviously flatworms do not do well with hot temperatures, would be sort of what we would take away from this. So I will give you another example of this that I found, so we can kind of look and see how else these equations can be tested. It took me forever to find this question, but here it is. So we have an AP Stat student designs an experiment to see whether the high school students are becoming too calculator dependent. She makes 2 quizzes, both which contain 40 questions that are best done using paper and pencil methods. A random sample of 30 students participate in the experiment. Each student takes both quizzes, one with a calculator and one without. To analyze the data, come here, stinky baby, he's making noise. To analyze the data, the student constructs a scatter plot and displays the number of correct answers with and without a calculator for each of the 30 students. A least squares regression line yields the equation bleh. Which of the statements is or are true? So let's just go through each of these individually. What I suggest for you guys is pause and you decide if 1, 2, or 3 is true, and then we'll come back together and look at them together. So hold on. So like I said, all of these questions are much easier if you have the formulas around. So the first one says, if the student had used calculator as the explanatory variable, the correlation coefficient would remain the same. So this is saying if we swap our x and y variables, that this would keep our correlation coefficient the exact same. So 2 ways we could do this. One is that we could, or my child is just going to make noise in the background. We are going to accept this. We could look at our formula sheet. The calculation for correlation coefficient is here. It involves multiplying basically the z-score for an x times the z-score for a y. Now, it doesn't matter what order we multiply two things in, right? This is the commutative property, which says that the order doesn't matter. So that's one way to think about it. The other is to think about what our correlation coefficient does. It tells us about the strength and direction of the relationship. So this is a slope that probably looks something like that. If we swap our variables, we're not going to change the strength nor the direction of that relationship. So number one is true. The correlation, it doesn't matter if you change units or if you swap your x and the y, we're still going to have the same type of relationship. In this case, since we have a positive slope, we're going to have a positive relationship. All right, number two, if the student had used calculator as the explanatory variable, the slope would remain the same. So now let's think for a second about our slope. Again, we can look back at our formulas. The slope is here. It's that b is r times sy divided by sx. If we change x and y, then we're going to swap that ratio on the b calculation. So it will actually change. You could also think of this as our slope is our rise over run. And so if we switch it upside down, we're doing run over rise or change in x over change in y instead. So definitely going to change there. As I was saying, oof, my child is trying to get to the keyboard. So this will be interesting. Our slope is the change in y over change in x. In this case, I think it was 0.89. And if we switch those around, it's going to be 1 over 0.89. So it will definitely change. The last one is probably the hardest. This says the standard deviation of the number of correct answers on the quizzes is larger than the standard deviation of the calculator quizzes. So this is basically saying S of y is greater than S of x. So again, if we look at our formulas, we can see this formula here. We know b is 0.89. Oops, I cannot. I'm trying to write with my left hand as I hold this baby away from the screen. R, was that given to us in the thing? R is 0.79. So we come back here. We have, I got to pick this up and hope for the best. Do not touch this baby. All right, so we know R is 0.8, B is 0.89, R is 0.79, and then SY, oh God, he's touching it. SY over SX, stop it. Oh God, you're a maniac. Over SX, and they told us, shit. That must be bigger than 1 because we multiplied a number 0.79 by 0.89, or we could divide over the 0.89. We can see this ratio has to be greater than 1. And so the answer choice here, the standard deviation of y is larger than the standard deviation of x, is true as well. So our correct answer would be E, that 1 and 3 are both true. Oh my gosh, I'm done with this because the baby is crazy.